Recently, the James Webb Space Telescope has unearthed a mysterious ancient galaxy, and it might completely change our understanding of the nature of dark matter and the process of galaxy formation. The telescope has managed to spot a stellar population bigger than our home Milky Way galaxy from 11 billion years ago, and it shouldn't actually exist. This galaxy is massive and is home to extremely old stars. They formed in the early universe. The problem is that this new observation upends our current cosmological models, since, by the time of the galaxy's birth, not enough dark matter had built up to seed such a formation. Researchers have been chasing this particular galaxy for 7 years. They spent endless hours observing it with the help of the two largest telescopes on our planet to figure out how old it was. Unfortunately, it was too faint and too red, so no one could measure it. Only after scientists moved their observations to space and started using the James Webb Telescope did they manage to confirm the nature of the galaxy. The thing is, unlike the Hubble Space Telescope, which orbits around Earth, James Webb moves around the Sun 1 million miles away from Earth. That's why it made it possible to see the galaxy clearer. Previously, astronomers were sure that in early cosmic times, there were very few huge galaxies. But recent findings challenge these theoretical models. Extremely massive dormant galaxies have been discovered as early as 1 to 2 billion years after the Big Bang and the beginning of the universe. The scientist who led the spectral analysis of the James Webb Telescope data said that they were doing everything possible to confirm the oldest galaxies that existed deep in the universe. When they did, it pushed the boundaries of the current understanding of how galaxies form and evolve. And now, the main question is how they managed to form so fast in the early universe, and what enigmatic mechanisms made them stop forming stars all of a sudden while the rest of the universe was still doing so. Galaxy formation is largely dictated by the concentration of dark matter. You see, around 84% of matter in the universe doesn't emit or absorb light. Astronomers call this stuff, which can neither be seen directly nor detected by indirect means, dark matter. It supposedly affects visible matter, radiation, and the very structure of the universe. Finding extremely massive galaxies so early in the universe is posing serious challenges to our standard model of cosmology. All because astronomers don't think that such monstrous dark matter structures as the ones hosting those massive galaxies had enough time to form. Researchers need more time to figure out how common such ancient galaxies are and how massive they can be. But if they manage to find more of those, it will really upset our ideas of galaxy formation. But it could improve our understanding of the physics of dark matter. Bizarre ancient galaxies aren't the only thing discovered thanks to James Webb. For example, scientists have long suspected that supermassive black holes could have existed in the early universe, and this theory has been proven only thanks to the JWST and its infrared eye. It showed that an ancient black hole within galaxy Sears 1019 was actively munching on all the matter it could lay its hands on. This hole is from the times when our universe was less than 600 million years old. And that's another mystery we're yet to crack. It's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. Astronomers were watching the galaxy hosting the unusually old black hole as part of the Cosmic Evolution Early Release Science Survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the ancient black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history.
Our home Milky Way galaxy has two very well-known satellite galaxies, the Large and Small Magellanic Clouds. They were named after Ferdinand Magellan, an explorer who led the first circumnavigation of the globe a whopping 500 years ago. During this expedition, two groups of clouds were discovered in the southern night sky. Those are now known as the Magellanic Clouds. But they're not the only ones. The Milky Way is surrounded by at least 61 other galaxies within 1.4 million light-years. For comparison, our neighbor, the Andromeda Galaxy, is 2.5 million light-years away from us. And still, astronomers think there are many more satellite galaxies, perhaps even too many. But first, let's figure out what a satellite galaxy is. Our Sun is just one of a truly huge collection of stars in the Milky Way. Hundreds of billions of stars orbit the center of our galaxy. But something much bigger orbits the Milky Way's center too: other galaxies. They are way less massive but have their own stars. We can compare the Milky Way to our Sun, and those other galaxies to planets. Astronomers call such formations satellite galaxies. The Milky Way's biggest satellite galaxy is the Large Magellanic Cloud. It's located about 163,000 light-years away and is about 1/100th the size of our home galaxy. Unlike the spiral Milky Way, the Large Magellanic Cloud doesn't have a clean spiral shape. One theory claims that it's because the Milky Way and other galaxies pull and warp it. In terms of distance, there are two candidates that can fight for the title of the closest satellite galaxy. One of them is so small that scientists consider it a dwarf galaxy. The other is so close that it's still debated whether it's a separate dwarf galaxy or part of our own galaxy. The satellite galaxy everyone agrees on is the Sagittarius dwarf spheroidal galaxy. It's around 50,000 light-years away from the center of the Milky Way. But there's a cluster of stars that is even closer than that. Some experts call it the Canis Major Dwarf Galaxy. It's likely to contain about 1 billion stars and is located so close to the edge of the Milky Way that it's actually closer to our solar system than to the galaxy's center. Some astronomers don't think the Canis Major is its own galaxy. They believe it's simply a dense area of faraway stars, which is still part of the Milky Way. Whatever the case is, this bunch of stars was once pulled toward the Milky Way by our galaxy's immense gravity. That's how most satellite galaxies in the area are likely to end up. Once, they might all merge into an even larger Milky Way galaxy. But let's get back to the assumption that the Milky Way has too many satellite galaxies. A team of astronomers has been hunting for such galaxies using the Subaru telescope. So far, they have searched a mere 3% of the sky. And still, they have found 9 previously undiscovered satellite galaxies. That's far more than they expected to spot. Interestingly, most of the satellite galaxies orbiting the Milky Way are newcomers. Yes, even the large and small Magellanic Clouds. This most recent research hopes to improve our understanding of our corner of the universe with the first detailed search for companion dwarf galaxies. However, the study also has another goal: to figure out dark matter distribution. You see, the current theory claims that the mass of our galaxy consists of 2 parts: visible matter, like stars and planets, and something invisible, which is hypothetical dark matter. We can't see it directly, but we can feel its gravitational influence through a certain distribution of mass in galaxies. Strangely, the simulation of the dynamics of the galaxy and this dark matter predicts hundreds of satellite galaxies in the Milky Way. Until recently, we only knew about a few of them, which created a contradiction known as the missing satellite problem. Hopefully, the new research will solve this problem. The team admits that so far their research has been based on statistically small numbers. Several assumptions have also been made based on a particular distribution of satellite galaxies. Follow-up studies of stars in the satellite galaxies and high-resolution imaging are definitely needed to progress further.
Attention! Attention! Emergency alert! This is not a drill. The Milky Way is on fire! I repeat, the Milky Way is on fire! Evacuation protocols activated. All terrestrial life forms are to be moved to the Andromeda Galaxy immediately. I repeat! Wait, a fire in our home galaxy? It all comes down to the incredibly hot gas surrounding the Milky Way. This isn't just intensely hot, it's also existed for billions of years. But what's heating this gas and keeping it that way? The Milky Way holds far more gas than stars, and this gas is crucial for forming new stars. Over billions of years, this massive reservoir has allowed the galaxy to keep producing stars. But this gas is incredibly thin and spread out, which makes it next to impossible to observe it directly. For a long time, this made it difficult to figure out how much gas the Milky Way really contains. But in recent decades, researchers finally confirmed that the galaxy is indeed surrounded by an enormous sphere of hot gas. This gas cloud extends as far as 700,000 light-years from the galaxy's center, and reaches temperatures of several million degrees. At first, scientists thought the gas's insane temperature was due to the Milky Way's gravity. They believed that gravity caused the gas to swirl around, keeping it from falling inward and heating it up in the process. But then, recently, scientists have discovered something even more surprising: a second layer of gas. And it's even hotter. How did we discover this gas with a temperature of around 18 million degrees Fahrenheit? Faint X-rays coming from all directions in the sky revealed the presence of this gas. The gas also showed up as it absorbed light from distant quasars, bright objects far outside of our galaxy. No wonder scientists began looking for the sources of heat that could explain this bizarre phenomenon. They soon found that the two types of gas, the X-ray emitting gas and the absorbing gas, came from different regions in the galaxy. The X-ray emitting gas is apparently produced by a puffed-up region around the Milky Way's stellar disk. This region is a direct result of the galaxy's star formation, which is still going on. Massive stars in these regions eventually explode as supernovae, releasing huge amounts of energy. This energy heats the surrounding gas to extreme temperatures. The gas heated by supernovae becomes turbulent, moving around chaotically. Some of it escapes into the space around the galaxy, while some of it cools down and falls back toward the disk. This continuous cycle of heating, cooling, and movement keeps the hot gas layer visible in X-rays. The absorbing gas is enriched with elements like sulfur, magnesium, and neon. These elements are created inside massive stars through nuclear reactions and escape into space during supernovae explosions. Runaway stars that are flung out of the Milky Way's disk also contribute to this process. When they explode as supernovae, they create pockets of enriched gas above the galaxy's disk. The X-ray emitting gas forms a glowing layer around the Milky Way's disk. This layer never disappears due to the star formation and supernova activity happening in the galaxy. Together, these processes explain both the absorbing and emitting signals observed by astronomers. Star formation, supernova explosions, and gas movement all work together to shape the Milky Way. The hot gas not only helps regulate star formation, but also redistributes materials created inside stars. And elements produced in stellar cores are spread throughout the galaxy by supernovae, becoming the building blocks for future generations of stars. The research team plans to keep observing the gas at other wavelengths of light. This might give us even more information about how the gas behaves and what it's made of. And once we understand the dynamics of this gas, we're likely to learn more about how galaxies like the Milky Way evolve over time. We need all the data we can collect after all. We don't even know the true shape of our galaxy yet. Recent discoveries have revealed that the Milky Way is not a flat disk as previously thought. No, it has a warped structure. And the craziest thing? Dark matter might be the cause of this deformation. The first confirmation that the Milky Way isn't a perfectly flat disk came from observations by the Gaia spacecraft. Gaia mapped the positions and movements of over 1 billion stars, and its observations showed that the Milky Way extends farther outward than initially believed. At its edges, the galactic disk was a wavy, warped structure with serious deformations along the outer edge. But what causes the warp? These deformations may result from ancient galactic collisions, like the Milky Way's collision with the Sagittarius dwarf galaxy around 6 billion years ago. However, a new study suggests another possibility. The warp might be caused by a tilted dark matter halo surrounding our galaxy. Dark matter halos are invisible, yet massive structures surrounding most galaxies, including the Milky Way. These halos contain most of a galaxy's mass and have a strong gravitational influence on the galaxy's structure. If a dark matter halo is tilted relative to a galaxy's plane, its gravitational effects could distort the galaxy over time. To figure out whether this theory is true, researchers used data from highly detailed computer simulations that modeled galactic evolution, seasoning the process with dark matter and interactions between matter and magnetic fields. The analysis revealed that the inner region of a dark matter halo can indeed tilt significantly with respect to a galaxy's plane. This tilt could result from galactic collisions or close encounters with other galaxies. Such crooked halos can stay this way for billions of years, which is long enough to warp the galactic disk. At the same time, this phenomenon isn't something unique. Astronomers have observed warped planes in other galaxies as well. In fact, nearly half of all spiral galaxies in the universe have warped disks. So, tilted dark matter halos and their gravitational effects might play a widespread role in shaping galaxies over time. While we're looking for answers, the Milky Way continues to shine brightly. But what kind of space electricity keeps its lights on? What fuels the process of star formation? After all, roughly one sun-sized star is born each year in the galaxy, and it needs a lot of fuel. Star formation requires hydrogen, the most abundant element in the universe. But it would still have been depleted long ago, unless there were a replenishing source. The source might be fast-moving hydrogen clouds raining down into the galaxy's disk. The hydrogen fueling the Milky Way is ionized, making it challenging to detect. Unlike atomic hydrogen, which emits light, ionized hydrogen does not. Instead, it absorbs light, which means it can only be observed when it passes in front of a bright background source. Before, astronomers used quasars, extremely bright distant space objects, as backlighting to detect these gas clouds. Unfortunately, in this case, it was impossible to determine how far away the clouds were. They could have been located anywhere between the Milky Way and the quasars billions of light years away. To pinpoint the location of the gas clouds, astronomers turned to the cosmic origin spectrograph aboard the Hubble Space Telescope. They observed 27 stars located within 10,000 light-years of the Milky Way's disk. They analyzed the stars' light and found that about half of the stars were obscured by gas clouds. It means they were close enough to directly feed the Milky Way's disk. The researchers calculated that the gas clouds contained a total mass equivalent to a whopping 110 million suns. This vast reservoir of hydrogen offers more than enough fuel to sustain the Milky Way's star formation. But where did those clouds come from? So far, it still remains a mystery. There are two main possibilities. The cloud might consist of hydrogen formed shortly after the Big Bang, primordial gas. These structures could have remained outside any galaxy for billions of years, only recently falling into the Milky Way's gravitational pull. Or the clouds might be made of material ejected from the Milky Way itself. When stars explode as supernovae, they can blow gas outward. Over time, this material could cool and fall back toward the disk, forming the clouds. We'll be able to figure out the origin of the clouds only after studying their chemical makeup. Gas from exploding stars contain heavier elements, while primordial gas created after the Big Bang is composed almost entirely of hydrogen and helium. Future ultraviolet telescopes could provide the detailed measurements needed to settle the question.
Our universe is like a giant highway, and galaxies are constantly moving along this highway. And just like cars driven by careless drivers, they can collide and crash. So, astronomers have recently witnessed such an incredible cosmic collision. It involved galaxies traveling at incredible speeds. Using advanced instruments, researchers clocked one galaxy traveling at a speed of around 2 million miles per hour as it crashed into a group of other galaxies. This collision has created shock waves that are so powerful they can completely reshape the entire region, leaving long-lasting effects on its structure and dynamics. Will it somehow influence our solar system? Before we find out, let's learn more about the region where this collision occurred. Actually, this collision is still happening in Stephan's Quintet. That's a fascinating cluster of galaxies that has been the subject of study for scientists for over a century. It's a group of 5 galaxies located in the constellation Pegasus. This group of galaxies was first discovered in 1877 by the French astronomer Édouard Stephan, who used a telescope at the Marseille Observatory. Despite its tranquil name, Stephan's Quintet is anything but peaceful. It's a chaotic spot filled with galactic collisions and turbulence. 4 out of the 5 galaxies are gravitationally bound. It means they are physically interacting with one another. Such interactions are ejecting material from the galaxies, and over time, it forms vast debris fields in the space surrounding the galaxies. Astronomers believe that, in the end, these galaxies will merge into one giant galaxy, but it will only happen in millions of years. The curious thing, though, is that the 5th galaxy in the Quintet, located in the upper left corner of images, is not part of the collision. This galaxy is much closer to Earth, more than 200 million light-years closer, to be precise. So its alignment with the other galaxies is just a chance perspective from our vantage point, making it appear as part of the group. Stephan couldn't know this in the 19th century, so the name Quintet has remained, even though only 4 galaxies are physically involved in the collision. Now, how about we look at this collision in detail? At the center of this event is one of the galaxies in the group, which is currently crashing into the others at a breathtaking speed. From our perspective on Earth, this galaxy appears to be approaching the Quintet from behind, heading directly toward the viewer. The collision is creating a massive shockwave that ripples through the surrounding galaxies. As the shockwave is moving through packets of cold gas, it's traveling at hypersonic speeds, several times the speed of sound in the intergalactic medium. This process strips electrons from atoms, leaving behind long trails of glowing ionized gas. But when the shockwave comes across regions of hot gas, it compresses the material rather than disrupting it. This compression produces radio waves, which can be detected by radio telescopes. While reshaping the structure of the intergalactic medium in Stephan's Quintet, this shockwave also influences the future evolution of the galaxies involved. Now, how did scientists even manage to spot such a dramatic space event? All thanks to innovative technologies. The most important participant was WEAVE, a cutting-edge spectrograph that's installed on the William Herschel telescope in La Palma, Spain. This tool specializes in gathering spectroscopic data, which is the information about how matter absorbs or sends out light and radiation. It allows astronomers to examine the movement and composition of space objects with great precision. Besides WEAVE, researchers have used data received from a few other large observatories. One of those was LOFAR, Low Frequency Array. It's a radio telescope with an antenna network observing the radio waves the weaker shock wave produced while compressing hot gas. Astronomers combined the data received from all these instruments and managed to study the shock waves and their effects in amazing detail. This collision in Stephan's Quintet gives us a fantastic opportunity to find out more about the interactions between galaxies, which can influence the evolution of the universe. You see, when galaxies crash into each other, their gas and dust gets redistributed, and it can trigger the formation of new stars and even cause central supermassive black holes to grow. And if we talk about Stephan's Quintet, the ongoing collision in this area helps us get additional information about the behavior of gas under extreme conditions. Now, at the same time, galactic collisions aren't as rare as you might think. They are common on a cosmic scale, and in the early universe, collisions occurred even more frequently because galaxies were located much closer together. With time, such interactions have played a key role in shaping the universe. Even our own galaxy, the Milky Way, has experienced tons of past collisions. We can see the evidence of such destructive interactions in the form of debris streams and disrupted star clusters within the galaxy. In fact, astronomers predict that the Milky Way will collide with the neighboring Andromeda galaxy in about 4.5 billion years, eventually forming a new, larger galaxy. Even though they're moving at incredible speeds, galactic collisions are super slow processes from our human point of view. While galaxies may travel at millions of miles per hour, the distances they cover are so vast that mergers take millions to billions of years to complete. Now, galactic collisions don't look like explosive crashes you might be imagining. Instead, they resemble when fluid merges. When two galaxies collide, their gravitational forces distort their shapes. They stretch and warp and exchange their material, stars, gas, and dust. As a result, tidal tails, rings, and even bridges between galaxies form. One of the most famous collisions between galaxies is ARP-148. During this cosmic crash, one galaxy became shaped like a ring, while the other stretched in a long tail-like form. That's how powerful gravitational interactions between galaxies during collisions are. But however impressive intergalactic collisions are, collisions between neutron stars, those ultra-dense remnants of massive stars, are among the most energetic phenomena in the universe. Neutron stars are incredibly small and dense. Just one contains the mass of our Sun packed into an area the size of a city. When two neutron stars collide, they often merge to form a black hole, releasing immense amounts of energy in the process. These events produce gravitational waves, ripples in space-time, that can be detected by instruments like LIGO and Virgo, as well as bursts of light that outshine billions of stars. On Earth, the possibility of a galactic collision directly affecting us is extremely low. Luckily, the timescales and distances involved make such events harmless to life on our planet. However, smaller-scale collisions, such as an asteroid impact, are more plausible. Asteroid impacts have occurred in Earth's history, and the most infamous of them caused the extinction of the dinosaurs 66 million years ago. And while large impacts are rare, astronomers closely monitor near-Earth objects to protect our planet from potential threats. Now, while we're talking about space collisions, a question may arise. Can life travel between planets? This is the idea of Lithopanspermia, the transfer of life between planets via debris from collisions. If an asteroid or comet hits a planet, fragments of rock could be ejected into space. If those fragments carry microbial life, they might land on another planet and seed life there. And guess what? According to experiments, certain super tough microorganisms like cyanobacteria could survive the harsh conditions of space travel, including radiation and re-entry into the atmosphere of another planet. In any case, lithopanspermia is still only a theory and a controversial one among scientists, but it doesn't make it less fascinating. It might eventually help us understand how life could have spread across the universe. But let's return to the ongoing collision in Stephan's Quintet. By studying such events, astronomers learn more about how galaxies interact, evolve, and influence their surroundings. Hopefully soon, we'll find even more interesting facts about this process. Stay tuned. Wow! Astronomers just discovered that the solar system is moving way faster than it should. One trusted cosmic speedometer says we're cruising at a normal pace. But a new one says we're racing through space at a speed that should not even be possible if our physics are right. So it seems that either something out there is pulling us, or one of our basic ideas about the universe is seriously wrong. Now, when we move, things in front of us react more than things behind us. For example, if we walk through falling snow, the flakes hit our faces, not the backs of our heads. Ride a bike, and the air pushes harder in front, while the air behind feels calm. The front gets busier, the back gets quieter. That difference alone is enough to tell our brain that we are in motion. In cosmology, this front versus back pattern has a technical name. It's called a kinematic dipole. Astronomers use this principle when they measure how fast our solar system is moving through space. To do this on a cosmic scale, astronomers look at the sky the way we look at the world when we start moving. Only instead of snowflakes or air, they use distant galaxies. These galaxies sit so far away, they barely change over billions of years. So they work like tiny markers frozen in place, perfect for spotting the difference between what's in front and what's behind. If the universe is smooth on the biggest scales, you'd expect the number of galaxies in each direction to be about the same. It doesn't really matter where the Milky Way is pointing or how we're spinning. The sky should balance out. But if our solar system is moving, one side might seem a bit more crowded because we're flying into it. It's the same trick as noticing more rain hitting the front of your jacket when you run forward. So, astronomers created huge maps of the sky using radio telescopes, which are good at picking up galaxies that shine in radio waves. Radio waves travel through dust, so the view stays clean. They counted how many radio galaxies appear in every direction to see if one side of the sky really is busier than the rest. And that's when they noticed something strange. The side of the sky we're moving toward was much more crowded than expected, like someone stuffed extra galaxies into that patch. This could mean we're moving faster than the standard model allows, or the galaxies are unevenly spread. We already know our motion from another source, the cosmic microwave background. It's the leftover glow from the Big Bang, and it works like a giant universal speedometer. For decades, it's given us a stable measurement of how fast the universe is moving. But this new result does not match that value at all. That extra crowding in the sky isn't supposed to exist at that level. Our best model of the universe says that when we zoom out far enough, the cosmos should look smooth and even. This result makes scientists scratch their heads. The pattern in the radio galaxy map was much stronger and more lopsided than expected. It lined up almost perfectly with the direction we're already moving, as if something out there was pulling harder than anything we've put into our models. Now, scientists just didn't look at one map and call it a day. They checked the result using several sky surveys made with different kinds of radio telescopes. One of those was LOFAR, a giant web of antennas spread across Europe that listens to the lowest, faintest radio signals, combined with two other large radio surveys. It's like taking 3 pictures of the same scene using 3 totally different cameras. If one of them added a strange color or distortion, the other 2 would catch it. But here, all 3 showed the same odd result. The dipole they measured is about 3.7 times stronger than what the standard model of the universe predicts. That's not a small calibration problem. That's a "your calculator must be broken" kind of difference. To understand how impossible this is, imagine checking 2 speedometers at the same time. One of them is the reliable one we always trust. That's the cosmic microwave background in this situation. It says we're moving at a normal speed. But the second speedometer suddenly claims we're going more than 3 times faster, like 200 miles per hour inside a parking lot. We would know something was off. Both readings can't be right. This is the problem. The CMB gives a solid decades-old speed, but the new radio galaxy result is showing something different. 2 measures that should match are telling very different stories. So, what could be the reason for these broken calculations? Well, one idea is that the universe is not as smooth or even on large scales as our model assumes. We expect that if we zoom out far enough, everything should start looking roughly the same. But this result hints that the large-scale universe might be more uneven than that. Maybe some huge regions are a bit richer in galaxies, while others are emptier, and those differences add up across the sky, creating a dipole stronger than the standard model predicts. If that is the case, the extra radio galaxies are not a mistake. They are a sign that the cosmos does not follow the straightforward pattern our model assumes. Now, another idea is that something genuinely huge and nearby might be pulling on our whole region of space. No, sadly, not some giant space monster messing with our system from another dimension. The universe already has giant walls of galaxies, long chains of superclusters, huge clumps of dark matter, and massive empty voids that stretch for hundreds of millions of light-years. These things are so large that they can change how entire regions of space move. It's not a sudden yank, more like a slow, constant tug on everything nearby over a very long time. If there's something like that close enough, we can't see it. A wide stretch of space is hidden behind the Milky Way's own dust and bright stars. Astronomers call this the zone of avoidance because our telescopes can barely look at what sits behind that glowing band. We already know there's a large concentration of mass in that blocked region called the Great Attractor, which was my nickname in high school. And some researchers think something even larger could be sitting deeper in the same direction. Now, if that's true, then the strange pattern we see in radio galaxies might not be a mistake. It could be the first hint that something huge is tugging on our whole galaxy region, and we simply haven't mapped that part of space yet. Finally, the third idea is that something is off with the model we use to describe how the universe works. A model is just a big set of rules, like a recipe. Our current one explains dark matter, dark energy, how galaxies spread out, and how the cosmos changes over time, and it expects the universe to behave in a smooth, predictable way on huge scales. The radio galaxy result does not fit that picture. It behaves like a number that refuses to match the rest of the equation, so scientists have to take it seriously. It could mean that matter and energy spread across space in a way we did not build into the model. That would not break physics. It would just mean the rules need an update. So, what happens next? A bunch of powerful new surveys are coming online, and even though they weren't built specifically to solve the dipole problem, they're going to be extremely useful for checking it. The Square Kilometer Array and the Rubin Observatory are all going to map galaxies in way more detail than the older surveys we use now. With cleaner, deeper data, these instruments may help us determine whether the strong dipole is real or fades away when we look at it with better tools. None of these are special missions made just for this question, but the next round of observations will test it naturally. If this strange motion turns out to be real, then something big is shaping our whole region of space. If it's not, then we just learned something important about how easy it is to fool ourselves with patterns in the sky. Either way, we get one step closer to understanding the universe and its puzzles. A chunk of rock from a different star system is heading straight toward Earth at a speed 1,000 times faster than a Formula One car. And I'm not talking about some sci-fi movie plot here. Recent research shows that our sweet little Earth could be more exposed to galactic intruders than we believe. These are called interstellar objects, or ISOs for short, and there is a certain part of Earth that has higher odds of getting hit. And we'll get back to it in a minute, but first, let's see what these ISOs are all about. We've only spotted a few so far, like One-Eye Oumuamua back in 2017, Two-Eye Borisov in 2019, and this year, Three-Eye Atlas, the third confirmed interstellar visitor, passed through our solar system. Interstellar objects like Three-Eye Atlas and Oumuamua aren't gravitationally bound to the Sun or any star in our solar system. That's why they're super fast and drift freely through the galaxy until they, by chance, cross our path. But what if one of those does more than just pass by and actually hits us? Scientists ran giant computer simulations with billions of fake interstellar objects flying around, then narrowed them down to the ones that could hit Earth. It turned out that these objects wouldn't hit the planet randomly. Low-latitude zones near the equator are more likely to get smacked. Places just above or below the tropics carry the biggest risk. And before you sigh with relief because you don't live there, there's also a bit more risk for the northern hemisphere, where almost 90% of the human population resides. It's likely to happen in a pattern and not as a random lottery because ISOs are not typical orbiters like asteroids or comets tied to the Sun. They come flying in on hyperbolic trajectories. That's a fancy way of saying they're unbound, just passing through. That means their arrival direction, speed, and relative motion all matter. The simulations show many ISOs are coming roughly from the direction the Sun moves in the galaxy, or along the Milky Way's main disk, called the galactic plane. Looks like the risk of impact also changes from season to season. The fastest potential strikes lean towards spring, when Earth is moving toward the solar apex. But overall, even calmer, slower ISO impacts are slightly more likely to happen in winter, when Earth faces away from that motion. It doesn't mean you should panic. These events are extremely rare, but it changes what we imagined. Astronomical visitor from the stars is no longer just a fantasy. It's a real risk, with a map. And this isn't just theoretical. Earth already gets hit by objects from inside our solar system all the time. Space rocks, comets, asteroids, they cross our orbit. That's why scientists keep an eye on near-Earth objects. Asteroids and comets that come within 30 million miles of Earth's orbit get that title and make it to the NEO list. To track them, scientists use a whole network of telescopes on mountains, in deserts, and even in space. NASA's Pan-STARRS in Hawaii scans the sky every night like a giant radar, takes picture after picture, and compares them. If something moves slightly between the images, that's a potential asteroid. The Catalina Sky Survey in Arizona does the same thing, and it found more than half of all near-Earth asteroids we know today. There's also NEOWISE, a space telescope that can spot dark, cold asteroids that ground-based telescopes might miss. And then there's DART, NASA's first real test of asteroid deflection. In 2022, NASA actually hit an asteroid on purpose to slightly change its orbit. The asteroid wasn't dangerous, but the test worked. And that single mission proved humanity can literally change the path of a space rock if we ever need to. And if all of this wasn't cool enough, NASA is building a new superhero to protect the Earth, NEO Surveyor. It will be the first telescope ever built specifically to detect huge numbers of asteroids and comets that could be dangerous to Earth. Here's why this thing matters so much. The solar system is crowded, messy, and full of objects we can't see with normal telescopes. A lot of asteroids are dark, like charcoal dark, and they barely reflect sunlight. That means regular optical telescopes look right past them. But even the blackest asteroid starts to warm up when the sun hits it, and warm things glow in infrared. That's where NEO Surveyor flexes. Its ultra-sensitive infrared detectors don't care how dark an asteroid is. If it's heated by sunlight, the spacecraft will spot it like a space detective with thermal vision. And the best part is that NEO Surveyor will finally see the asteroids that come at us from the direction of the sun. Ground-based telescopes can't stare at the sun unless they want to go blind. So anything approaching from that direction is basically sneaking up behind Earth wearing cosmic camouflage. NEO Surveyor fixes that. It will also catch the sneaky objects that travel ahead of Earth or behind us in our orbit, the ones that are drowned out by sunlight and slip through the cracks. These are real threats, and bigger telescopes on the ground often miss them. But when they don't miss a new object, they track it for days or weeks to figure out its orbit, basically its path around the sun. They need to know if it's going to cross Earth's orbit, if it will come close, and if so, how close. If it doesn't look harmless, it will go on to the Sentry Risk Table, which is basically Earth's cosmic watch list. So, stuff hits our atmosphere all the time. Tiny meteoroids, something like cosmic crumbs, burn up and give us shooting stars. Sometimes a slightly bigger rock shows off and creates a bright fireball. It happened over northern France a couple of years ago. Astronomers spotted a small asteroid hours before it arrived, and people on the ground got a surprise fireworks show courtesy of outer space. But every now and then, a rock comes in that's not quite big enough to survive the descent, but still large enough to release a terrifying amount of energy when it breaks apart. One example of those was the Chelyabinsk meteor. On February 15, 2013, the locals were just starting their day when the sky suddenly lit up. When it blew up about 14 miles above the ground, it released the energy of 440,000 tons of TNT. Then, a space rock, only the size of a house, slammed into Earth's atmosphere at 11 miles per second. And for a moment, it looked like a sci-fi movie had come to life. The shockwave shattered windows across almost 200 square miles, damaged thousands of buildings, and injured more than 1,600 people, mostly from flying glass. And because it came from the direction of the sun, no telescope ever saw it coming. The crazy part is that it wasn't even close to the kind of destruction a bigger asteroid could do. NASA's planetary defense experts still talk about this meteor like it was both a warning shot and a wake-up call. After this episode, NASA and international partners launched the International Asteroid Warning Network and the Planetary Defense Coordination Office, the folks whose job it is to make sure Earth doesn't get surprise smacked again. NASA is planning rapid response missions to study any asteroid that looks suspicious, and they might even send a spacecraft to check out an asteroid making a super close pass in 2029. Think of it as our planet doing regular health checkups against space hazards. The odds for any person, anywhere, to be hit by an interstellar rock in their lifetime are still minuscule. But what used to seem like science fiction, rocks crossing between stars randomly hitting us, now looks like science fact, or at least science possibility. So the more we understand how asteroids respond to impacts, the better our chances of saving Earth one day. Because you can't protect humans from a dangerous asteroid if you don't know it exists. The equipment that's getting more and more advanced gives us the advantage of time, and in a cosmic emergency, time is everything. Oh man, the sun did it again! It just blasted a huge cloud of plasma into space. This time, it was one of the fastest and most powerful eruptions of this solar cycle. It was so strong that the shockwave hit Venus, our next-door neighbor. That's when scientists got worried and started asking a scary question. Could Earth be next? Well, let's just cut to the chase. If your GPS and internet have been working fine over the last few weeks, and your city hasn't had any big blackouts lately, you already know the answer. No, that powerful blast didn't hit Earth. Or at least we didn't feel any real effects from it, because this event happened in October 21, 2025, and if our planet had been in its path, we would have felt the effects only a few days after that date. You see, we're talking about coronal mass ejections, or CMEs. From time to time, the Sun throws a giant cloud of superhot plasma into space, straight from its outer layer, the corona. Think of plasma as a superheated gas. It's what the Sun is made of, and it's full of tiny charged particles, positive ions and negative electrons. These outbursts happen because the Sun's magnetic field is always moving and twisting. Sometimes the magnetic lines get tangled up, then suddenly snap and reset. This process is known as a magnetic reconnection. And when that happens, boom, the Sun launches a CME. A single coronal mass ejection can throw billions of tons of material into the solar system in one shot. And it can create a shockwave. That shockwave can speed up charged particles, which raises the chance of a radiation storm. And if a planet is in the way, yeah, that can be trouble. The tricky part is that CMEs are pretty unpredictable. They can blast out in different directions, and they don't all move at the same speed. The fastest ones race through space at millions of miles per hour. If one is aimed at Earth, it can get here in as little as 15 hours. Slowest ones can take days to get here, but even then, it's usually somewhere between 1 and 5 days. It's not like months. Since this big blast happened a while ago, it's safe to say that, well, we're safe. And honestly, even if it had hit Earth, we'd probably be safe anyway. Sure, a strong CME can mess with satellites, disrupt radio and internet signals, and even knock out power grids for a while. But it's not the kind of thing that ends the world or wipes out humanity. So take a breath. Even a really powerful solar eruption isn't going to destroy Earth. Unfortunately, we can't say the same thing about Venus. CMEs hitting our neighboring planet are actually one of the reasons Venus can't support life, at least not what we consider life. But don't worry, we'll get to that part later. First, let's dive into this recent solar outburst and what made it so extreme. This one came from the far side of the Sun, the side we can't see from Earth, and it came from an especially active sunspot area called 4246. This is a new, huge, messy sunspot that's been responsible for the latest round of solar storms headed our way. The big blast happened right after that region rotated past the Sun's western edge, so it was out of view from Earth and from most weather satellites. Thankfully, the event was caught by an instrument on a NOAA satellite called CCOR-1. Think of it like a special camera designed to spot big solar blasts even when they happen on the far side of the Sun. That's why it's strategically placed so high above Earth, and it orbits about 22,000 miles over the equator. The CCOR-1 manages to capture those images by blocking the Sun's blinding surface, so it can see the faint glow around it and track huge plasma clouds as they spread out into space. Now, let's talk about speed. NASA estimates that the CME in October was moving at about 820 miles per second. But the first radio signal suggested it might have been even faster, close to 1,537 miles per second. Trust me, that's crazy fast for a coronal mass ejection. To put that in perspective, only a handful of blasts in modern history have been quicker. One famous example happened in 2017 during an X-class flare rated around X8. So according to NASA, X-class means the strongest kind of solar flare. The number tells you how strong it is. An X1 is the baseline, an X2 is twice as strong, an X3 is 3 times as strong, and so on. So yeah, an X8 flare is something huge. Back on Earth, that 2017 event did mess a bit with high-frequency radio signals for a while. But for us, that was pretty much it. Mars was a different story. When the same event hit the red planet, it heated the upper atmosphere in an uneven way. In the hottest areas, scientists saw the top 2 layers, the thermosphere and the ionosphere, start interacting more than usual because of the blast. And that had a real effect. Oxygen began escaping into space much faster than normal. In other words, that brief event made Mars lose part of its atmosphere at a higher rate. Now, when we talk about this recent burst, the story is kind of similar, but with a twist. This time, Mars wasn't the main target, Venus was. The planet was sitting right in the path of the solar burst. So when the blast hit, Venus got slammed with a storm of charged particles. Now you might be wondering, why is it a bigger problem when a solar eruption hits planets like Venus or Mars, but not as big of a deal for us here on Earth? Well, it's because of Earth's magnetic field. So big blasts from the sun can mess with the atmosphere around a planet. But on Earth, a lot of that impact gets blocked by a natural magnetic bubble called the magnetosphere. Good thing, huh? Here's how it works. A wave of plasma comes from the sun and slams into the magnetosphere, the region around Earth controlled by our magnetic field. That magnetic field pushes most of the charged particles away, kind of like a shield, but not all of them. Some particles still sneak through and crash into the upper atmosphere. When that happens, we can get geomagnetic storms. These storms create amazing auroras. They can also mess with satellites and communication networks, like we talked about earlier. But some planets, like Venus, don't have a strong magnetic field like Earth does, and that can be bad news. Because when a CME wave reaches Venus, the charged particles crash straight into the atmosphere and, over time, slowly peel parts of it away. Now here's a real example. On December 19, 2006, the Sun released a small, slow CME. Even though it wasn't moving fast, it was still strong enough to do damage. About 4 days later, it reached Venus and ripped away a large amount of oxygen from the planet's atmosphere, sending it off into space for good. Or bad. And this is actually one of the big reasons why planets like Venus are uninhabitable. Without a strong magnetic field, CMAs can slowly strip away their atmosphere, blast the surface with dangerous radiation, and create brutal space weather conditions. Venus is a perfect example. It is the hottest planet in our solar system, being 100 times hotter than Earth. Its atmosphere is insanely thick, and the pressure over there is insane, so much so that the longest any spacecraft has survived on its surface before being crushed is a little over 2 hours. Scientists think that getting hit by solar eruptions without a proper magnetosphere to protect it helped push Venus toward this extreme world. And by studying what happens to planets like Venus, we can learn something bigger: how important a magnetic shield might be for life on other worlds we find outside our solar system.